Hello, welcome to Module 2, Unit 4, where you will learn how to build the causal loop diagrams on a real case. My name is Giovanna Taviani Olmo. I'm a researcher at the Norwegian Institute of Bioeconomy Research.
And I'm Divina Gracia Pagkaliwagan Rodriguez, and I'm also a researcher at NIBIO.
So, in the previous units, Flor and Clementine introduced the causal loop diagrams, or CLDs, and the value network analysis as tools to understand complex systems. They discussed the variables, the feedback loops, and how the systems behave over time. But understanding the method is only the first step. To really grasp systems thinking, we need to apply this to a real case situation.
So, in this unit, we move from theory to practice. We will build a causal loop diagram step by step using a real case from the Emphasis project, the Irish Organic Dairy System. The goal is not just learn how to draw a diagram, but to learn how to think differently about problems. Because causal loop diagrams are not just visual tools. They are a way of structuring how we understand complexity, how we identify patterns, and ultimately, how we design better interventions. Let's start with the core challenge. Ireland has very favorable conditions for organic dairy production. As introduced in the previous unit by Clementine, you learned that organic dairy delivers multiple environmental benefits, including improvements in biodiversity, water quality, climate performance, and animal welfare. Economically, it can also be competitive with conventional systems. In some cases, organic farms are among the most profitable on a per-liter basis. And yet, organic dairy still represents only a small share of total production. A key challenge is the conversion period, during which farms must comply with organic standards but cannot yet sell their milk as organic. This creates financial risk. So, the question is, why does the system not scale despite favorable conditions? At first glance, we might think of individual barriers, such as costs, risks, or lack of knowledge. But these factors are interconnected. Farmers' decisions depend on markets. Markets depend on infrastructure. Infrastructure depends on investment. Investment depends on policy signals. And policy depends on system outcomes. This is not a simple problem. It is a system. This is why we use a causal loop diagram, to understand how these elements interact and evolve over time. Before building a causal loop diagram, we first need to define the system we are analyzing. A system is a set of interconnected elements whose interactions shape outcomes over time. Here, we are not analyzing the entire Irish agriculture food system. Instead, we focus specifically on the transition from conventional to organic dairy farming. Our central question is, what influences farmers' decisions to convert, and what enables or constrains the growth of the organic dairy sector? Defining this boundary is essential. Without it, the system becomes too complex to analyze meaningfully. In practice, we include the key variables and interactions that shape system behavior, while excluding less relevant elements. System boundaries are not fixed. They can be refined as our understanding evolves. The next step is to identify the actors involved in the system. This builds on the value network analysis introduced in the previous unit. In our case, the main actors include farmers, advisors, policymakers, certification bodies, processors and distributors, and of course, consumers. Each of these actors play a role in shaping the conditions under which organic dairy can develop. When building a causal loop diagram, the focus is not on mapping actors directly, but on capturing the variables and relationships they influence. In some cases, actors can be represented explicitly, but most often they are reflected through system variables such as incentives, knowledge, or market demand. So, this step helps us ground the analysis in the real-world structure of the system.
Now we move to one of the most important steps in building a causal loop diagram. So we have to translate actors and case insights into variables. Variables are the elements that can increase, decrease, or change over time. They represent the conditions, processes, or outcomes that shape system behavior. In this case, examples include farmers' motivation, policy support, market demand, economic returns, training, and advisory service. This step is critical because if variables are poorly defined, the causal loop diagrams becomes weak or confusing. A good variable is clear, measurable, at least conceptually, and is something that changes over time. Once we have variables, we can then begin to connect them. So to start building the diagram, we select a manageable number of variables. If we try to include everything at once, the system becomes unreadable. So we begin with the core set, which is policy support, advisory service, farmer motivation, conversion practices, certification, market demand, economic returns, and infrastructure. This selection allows us to capture the main dynamics without overwhelming complexity. These variables, in fact, capture the key dimension of the system, which are the decision-making, the market dynamics, and the structural condition of the system itself. So we will build the diagram using these variables first, and later we can expand the system, including additional relevant variables such as the rate of conversion, the efficiency of the supply chain, the market conditions, and finally the environmental impact, or better, its reduction. Now we start connecting the variables. So we can begin with the simple and logical chain. For this, we use VenSim, and in the last slide of this section, you will see how to do it in practice. VenSim is a program that you can use to do this. Is not the only one, but it could be maybe the one that is of your choice. So we begin with a simple and logical chain, which is connecting policy support with advisory service, and then farmer confidence and motivation. Higher motivation, of course, then leads to more farmers adopting conversion practices, and this leads to more organic certification. But this is not yet the full system. It is just the starting storyline. This approach is very important because CLDs should not be built all at once. They should be built step by step, and this is what we're going to do here. So next, we can extend the chain, as we said before, linking the organic production with the supply and visibility, strengthening market demands for organic dairy. And then with higher demands comes more economic return, and better return increases farmers' motivation. Now we have created our first feedback loop, which you will see later on. This is a reinforcing loop, a loop that can drive growth, But it also shows that if one of the elements is weak, then, for example, the demand, the whole loop may not activate. But the system does not depend only on farmers and market. So we need to also take into account the infrastructure. So even if farmers are motivated, they need systems that are supporting them. And this is where infrastructure is becoming critical. If demand increases, there is more incentive to invest in processing and supply chain capacity. And better infrastructure can improve this efficiency. And this improves, again, economic returns. This shows that the system change depend on both individual decision and structural conditions. So let's now make the reinforcing loop explicit. Market demand increases economic returns. Economic returns increases farmer motivation. Motivation increases conversion. Conversion increases certification. And certification supports market demand. This is a reinforcing loop. This loop explains how the system can grow, but also explains why growth may not start. Because if one of the elements is missing, the loop, so the mechanism, does not activate. Not all loops reinforce growth, though. We have to understand this. Some loops stabilize the system. And in the Irish case, this comes about with policy, where policy plays the role of stabilizing the system. As the system evolves, policy may adjust based, for example, on environmental or economic outcomes. And this prevents uncontrolled growth and ensures alignment with broader objectives. Balancing loops, which you can see here on the left side of the screen, are essential because they prevent systems from moving endlessly in one direction. They introduce regulation and correction and stability into a system. Okay, now, as you can see, we have Vensim open on the screen, and this is our program of choice for building the causal loop diagrams. I have been preset all the variables, which you can build by clicking on the box of variables there, and then you can write them. And then we can start to connecting the variables. So we begin with the simple and logical chain, connecting policy support to advisory service. These two variables, they move in the same direction because policy support, if it increases advisory service. So we put the plus. Then better advisory services increase farmers' confidence and motivation, which is a bit lower on the screen. And they also move in the same direction. So we will put the plus also in here. Then we have higher motivation leads to more farmers adopting conversion practices. So also this is going to be positive. And this leads to more organic certification, which is also positive. But this is not yet a full system. It's just a starting of our storyline. So then we can extend the chain with more certified organic production, increasing the supply and visibility. So also this is positive. This strengthens market demand for organic dairy, and higher demand improves economic returns, which is also positive. So then we go to increase returns or better returns, increase again farmers' motivation. So we go back to the original variable. And by doing this, we create the first feedback loop. And this is a reinforcing loop, a loop that can drive growth. So if we continue then connecting, we can see that if demand increases, there is more incentive to invest in processing and supply chain capacity. So here we can then include the infrastructure. And better infrastructure improves efficiency, which then improves economic returns as well. And this shows that system change depends on both individual decision and structural conditions, as we said before. So now we can make the reinforcing loop explicit. So market demands increases economic returns increases farmers' motivation increases conversion increases certification, and certification supports market demand. Another reinforcing loop. This loop explains how the system can grow, but also explains why growth may not start. Because if one of these elements is missing, the mechanism does not activate. But not all loops are about growth. Some loops stabilize the system. And this is what we're going to look now. In the Irish case, policy plays this role, as we said. So the system evolves, and policy may adjust based on the environmental or economic outcomes. And this prevents uncontrolled growth and ensures alignment with broader objectives. Balancing loops are essential because they prevent system from moving into just one direction. And they introduce regulation and correction, stability into our system. So as you can see here, this is the balancing loop that we have.
Now, we move to a key concept. A barrier is a single obstacle. Example, a lack of knowledge, low market demand, limited infrastructure. These are important, but they are not enough to explain why change is low. A lock-in, instead, is a set of interconnected barriers that reinforce each other. It is not just a problem. It is a self-reinforcing structure. In our example, if market demand is low, prices remain low. If prices are low, economic returns are weak. If returns are weak, farmers are less motivated to convert. If fewer farmers convert, supply remains limited with limited supply. The market does not grow and we are back to low demand. This is not a chain. It is a loop. And that loop locks the system in place. And this is why change is difficult, because the system maintains itself. In this system, we can identify several types of lock-ins. First is the economic lock-in. So low demand leads to low returns that leads eventually to low motivation, and that low motivation leads to low conversion. And then it leads to low supply and low demand. This keeps the sector small. The second lock-in is the knowledge and capacity lock-in. Limited advisory support leads to low confidence, low adoption, and then limited experience that eventually leads to continued low confidence. This slows learning and innovation. And the third lock-in is the infrastructure lock-in. Limited processing capacity leads to weak supply chains, which leads to limited market access, then low investment, and then continued infrastructure gaps. This constrains scaling. And the fourth is the policy dependence lock-in, which means the dependence on subsidies can lead to uncertainty about long-term viability, and then leads to cautious farmer behavior that slow transition. And this creates instability in decision making. So, lock-ins are not isolated. They are interconnected. Economic lock-ins reinforce infrastructure lock-ins. Infrastructure lock-ins reinforce market lock-ins, and market lock-ins reinforce farmer behavior. This creates a system of lock-ins. If we treat this as a separate problem, we risk designing ineffective solutions. For example, investing only in training will not work if markets are weak. Increasing demand alone may fail if infrastructure cannot support it. We need to intervene in a way that breaks the reinforcing structure. This is exactly why we move next to leverage points. Because leverage points are not about fixing individual barriers. They are about unlocking the system. Lock-ins are the reason systems stay stuck. Understanding them is the first step to changing them. Now that we have mapped the system and identified the feedback loops, the next step is to ask a very practical question. Where can we intervene to change the system? This is where the concept of leverage points becomes central. A leverage point is not just any intervention. It is a place in the system where a small, well-targeted change can produce larger systemic effects. Leverage points are places where intervention shifts the system. We target high-impact areas. A good leverage point has 3 characteristics. It influences multiple variables at once. It sits within a feedback loop. And lastly, it can shift the direction or strength of that loop. So, we are not just asking, what can we change? We are asking, what change will cascade through the system? In this case, 1. Training and advisory services. Improving advisory services does more than increase knowledge. It increases farmer confidence, reduces perceived risk, improves implementation of organic practices, and it strengthens motivation. This directly strengthens the motivation conversion loop. The second is the infrastructure and processing capacity. Investment in infrastructure enables more efficient supply chains, reduces bottlenecks, improves market access, and increases economic returns. This activates the market infrastructure reinforcing loop. Without infrastructure, even motivated farmers cannot scale. Third is the market development and demand creation. Strengthening demand through branding, consumer awareness, retail strategies leads to, for example, higher prices, more stable returns, stronger incentives for conversion. This is critical. Why? Because demand is one of the entry points into the reinforcing loop. Fourth is the policy coherence and long-term support. Policy is not just a driver, it is also a regulator. Well-designed policy reduces uncertainty, aligns incentives, supports advisory systems, and enables investment. Policy is a meta-leverage point. It shapes several other variables simultaneously.
So, to conclude this unit today, what we did was not just drawing a diagram, because we did frame the system. We used the actors, identify their role and what they exchange to translate them into variables, build the causal relationship, identify the feedback loops, and interpret the system behavior. This is system thinking in practice. So causal loop diagrams help us move from complexity to insight, and from insight to action.
Now, are you ready to reconstruct this CLD? So in the previous units, you have seen how we analyze the system using the value network analysis and a causal loop diagram. So in this exercise, you will work with a set of stakeholder interviews to analyze the system yourself. These interviews provide partial insights into how the system operates. Your task is to use this information to identify key elements and interactions, and to understand why adoption remains limited despite favorable conditions. Okay, so start by reading the stakeholder interviews we have prepared for you. And from this, identify key variables, both explicit and implicit, and map how these influence each other. Then identify feedback loops that help explain system behavior. In parallel, map the actors and the flows between them to represent the value network. Since the information is partial, your diagrams do not need to be complete. The objective is to develop a structured understanding of the system based on the available evidence. The goal is not to produce a perfect model, but to reason the system using incomplete information. So, good luck!
Bye.